So this video is going to focus on the atom. There's a fair amount of content in it, so I'm going to try to go through it as quickly as I can. Feel free to stop it wherever you need to. Overview of the atom. Protons, neutrons, and electrons are found in it. The protons and neutrons are in the nucleus. The electrons are localized outside the nucleus in orbitals. Protons are positive, neutrons are neutral, electrons are negatively charged. The mass of a proton and neutron is pretty comparable, but electrons are much, much lighter. So when we talk about the atomic mass of an element, we are pretty much focusing on the protons and neutrons since they make up the vast majority of the atom's mass. Protons are always able to be determined for any element as long as you have a periodic table. If you don't have a periodic table out, I would strongly encourage you to get one. Every element has a unique number of protons, and that's where those atomic numbers on your periodic table come into play. Neutrons allow us to distinguish between an element's isotopes. There are different forms of the same element that exist, and in their atomic form or in their ionic form, how they differ is the mass that's present in their nucleus. Since the protons can't change, it's got to be the neutrons. Some isotopes are found in greater abundances than others. It's part of the reason that carbon's mass is super close to 12, because although carbon has 3 isotopes, 12, 13, and 14, carbon-12 is found over 99% of the time in nature. So we'll talk a little bit more about how we get those average masses in subsequent slides. But every element's isotope has a unique mass number that is determined by the sum of its protons and neutrons that are present. Finally, with electrons, electrons play a key role in our chemical reactions because those are the ones that are transferred or shared so that elements can combine to form compounds, or those are the ones that have to have bonds broken for them to be able to reform into their elements, or to make simpler compounds, or just to make different compounds. Atoms will always have the same number of protons as they have electrons because they are electrically neutral, while ions will have a different number of electrons than protons. Ions that have more protons than electrons will be called cations. They are positively charged, while anions will form when you have more electrons than protons because you are negatively charged. So this says it's a complete atom symbol. This also is not just going to apply to atoms, it applies to ions as well. And you see that in the example I have for you on the page. If you look at this, you will see that there's always going to be numbers in certain locations around the element symbol. That's the X. The A, the top left-hand corner, will always be representing the mass number, so telling you what isotope you have for that given element. It's protons and neutrons. Z will always be found in the bottom left-hand corner, your atomic number, which is going to be unique for each element, your number of protons. And then finally, C, if you have an ion, will be placed in the top right-hand corner. And you will need to put a plus or a minus to indicate whether it's a cation or an anion, and that's just the difference between your positive protons and your negative electrons. If it is a neutral atom, the charge would be 0, and you are welcome to write that 0, or you can just leave it blank, understanding that if nothing is written, that you have a neutral atom present. So here are some examples that we're going to work through. Again, if you don't have a periodic table out, I would encourage you to get one because that's going to help you get where some of these numbers are coming from. In the first example, we have fluorine as an atom, and we're told it has 10 neutrons. By telling you it's fluorine, if you look on your periodic table, you're going to find that it is number 9 atomic number-wise, and that means that it has 9 protons. Because it is an atom, its protons have to equal its electrons, and its charge has to be 0. When I write its chemical symbol, the symbol for fluorine, F, would go in the center. The bottom left-hand corner would be its protons, its atomic number 9. The top left-hand corner would be the protons plus the neutrons, 19. And then because this is neutral, you could put a 0 in the top right-hand corner, or you could leave it as is. When we're naming isotopes, we want to name it by the element as well as its mass. And remember that the mass number for an isotope is determined by its protons and neutrons. So when I name the isotope for this particular atom of fluorine, it would be represented by fluorine 19 to indicate the number of particles that are present in its nucleus. In my second example, I have an oxygen ion. We're going to follow the same kind of logic that we did in the first one. We have neutrons again, and we're told it has a charge. You didn't necessarily have to be given the charge for oxygen because oxygen's always going to be -2, but not too bad to review that for right now. So when I look for oxygen on my periodic table, I'm going to see that it's number 8. Because it had 8 protons and a -2 charge, I know it had more electrons than protons, and that had to be a difference of 2. So that meant that I had 10 electrons present, so that it was a negatively charged ion. The symbol will be represented by the element O, the atomic number 8, its protons in the bottom left-hand corner. 8 plus 9 gives me my mass number, 17, the protons plus the neutrons. And this time I absolutely have to write the charge because it is an ion. If you write it as 2-, that's not going to have any issue in terms of grading. -2, 2-, they are interchanged quite often. -2 is charge, 2- is oxidation state, and for all practical purposes, they mean the same thing. To name the isotope, again, the name of the element with a dash and then its mass number, so oxygen 17. Our third example is a little different because you don't have the name of the element, nor do you have its protons. You have its neutrons, you have its electrons, and you have its charge. Well, if I know the charge and I know its electrons, I should be able to find its protons, because if it's positively charged, that means it should have one more proton than its electron, in this case with the charge being +1. So I would add 1 to 36 to get 37 protons. You would not be able to find the number of protons without that extra information, and I will always give you enough to be able to find whatever pieces you're looking for. By knowing that it's number 37, I should be able to look on my periodic table and I should find that it is rubidium. And because it has a charge, it is actually an ion as opposed to an atom. I'm going to work on the symbol now, Rb in the center, the protons, the bottom left-hand corner, its atomic number, 37. Top left-hand corner would be my protons plus my neutrons, 84. And then the top right-hand corner would be my charge, which in this case would be +1. So to name this isotope, it would be named after its mass number, rubidium 84. In the final example, I gave you the isotope name and I gave you the charge. This is the first time I didn't give you neutrons. So we're going to see how you can get neutrons from this information, or how if you had the number of the mass number, you could use that to find neutrons. Silver 108, looking at my periodic table, tells me that it has, this is atom because it's neutral, so silver atom. But if I look at my periodic table, you will see that it has 47 protons. The mass number is the protons plus the neutrons, so I can use that to help me find neutrons. But because it's an atom, I know it's neutral, so it also has 47 electrons. Whichever way you want to do it, you could have found the neutrons first. I need to take the difference between 108 and 47 to get my neutrons, 61. And now I can write the elemental symbol. Ag for silver. Bottom left-hand corner would be my protons, 47. Top left-hand corner would be my mass number, 108. And again, you do not have to include the charge. If you want to write anything, you could write it with a 0. The second part of the atom we're going to talk about is atomic mass. I told you that the atomic masses on the periodic table are not just based on an isotope. They're based on all of the naturally occurring isotopes for a given element and the relative abundances we find them in nature. Oftentimes, those relative abundances are written as percentages. So this is similar to calculating a grade on a percentage scale. You have to account for the proportion that each isotope is contributing to that average mass. So we need to take that percentage and turn it back into a fraction. We do that, multiply the mass of each isotope by its relative percentage, divided by 100 for all the isotopes that are naturally occurring for that element, and then we add those masses together to get the overall average mass. So in our first example here, we have 4 isotopes for chromium, 50, 52, 53, and 54. And we're told the relative percentages that we find those isotopes present naturally. To calculate the average mass, we're going to take each of those mass numbers, multiply them by their percentages, find the relative fraction of mass each isotope is contributing, and then sum them together. So for 50, I added AMU because those are, it says the questions, what's the average atomic mass of chromium in AMU? That's what the units would be if we weren't dealing with lots of particles, which is what we normally do with these masses. We tend to deal with grams. But we are totally fine using AMU for this. That 50 is an exact number because you're counting the protons and neutrons. I will tell you for atomic masses, unless I direct you otherwise, you can plan to round to 2 decimal places. So we're going to do that for the other 3 isotopes. There's 52 AMUs for chromium 52, so 83.79% of the time. 53 AMU for chromium 53, 9.5% of the time. And then finally 54 chromium, which is present 2.37% of the time. Just like we talked about earlier on, you need to follow order of operations, do your multiplication first, and then do your addition. Again, none of the mass numbers have sig figs attached to them. They are exact values. So when I asked you to round these to 2 decimal places, you should have gotten relatively these masses for each of the products that you needed to multiply together. And then when I add them, I get an average mass of 52.07 AMU, which I do believe is fairly close to what you will find for chromium on the periodic table. So that's more straightforward if you just want to find the average mass. You could also use this to figure out what those abundances are, depending on the number of isotopes you have present. Here we're told nitrogen has 2 naturally occurring isotopes, nitrogen 14 and nitrogen 15. I'm accounting for a mass defect, which occurs to help to hold the nucleus together. So you're given exact masses. These would have sig figs attached to them, 14.003074 U, another way to write AMU, and 15.000108 U. Okay. To find the percent abundance, rather than solving for Y, we're solving for X. So we're going to need to know how we can solve for those abundances in terms of X. Nitrogen 14 and nitrogen 15 together have a percent abundance of 100. So if we were going to go back to fractions, they would have an abundance of 100 divided by 100. So if I let one of them solve in terms of X, like let's say 30%, the other one would need to be 1 minus that, 70%. So we can set them in terms of one another and only have one variable in our equation. I've given you 2 versions of the periodic table. I've given you the one that you probably used in your first chemistry class, and I've given you the one that they allow y'all to use on the AP exam. The average mass of nitrogen, I believe on the one that you used previously, was 14.007. I went on an extra decimal place just to give you a little bit more information on this. Okay? So instead of knowing Y or solving for Y, we're given Y, that 14.007. So I'm going to set this up just like I did the problem previously, but the 14.007 will be what I am setting everything equal to. Then I take the mass of each of my isotopes and I multiply them by their relative abundances. So nitrogen 14 gets multiplied by X, nitrogen 15's mass gets multiplied by 1 minus X. And at this point, I start to combine like terms together. I need to distribute that 15.000108 U through, and then combine the X terms and combine the constants. So the first term's not going to change, but the second one is going to end up with 2 terms. And so the U's would come together and the X's would come together. So if you go back and do that algebraically, you'll see that. You'll notice in the directions I said round your answer to 2 decimal places. I'm not going to get picky about sig figs with these because I know the numbers can be a little bit out of control. So I asked you to round it to 2 decimal places. Go for it with that. So when I divide 0.997034 into 0.993, I get that X is 0.9931. Okay. So with that in mind, if I want to know the percent abundance of nitrogen, this is just the relative abundance of nitrogen, I would multiply it by 100. And if you think about it, look where the mass is. It was ridiculously close to nitrogen 14. So it makes a heck of a lot of sense that the percent abundance was pretty much all nitrogen 14. Your average masses should always fall between your lowest and your highest isotope masses. So we should never have gotten an answer below the 14.003074, and we never should have gotten an answer above it for our average mass. And that was indeed the case. So the last topic we're going to talk about, sorry this video is so long, is just a little bit about history of the atom. We're not going to spend a whole lot of time on this, but I just think it's kind of neat to see how science can be applied to what you're learning right now. In terms, we hear all of the terms about hypothesis and theory. Well, the atom model is an excellent case study of that. There are 5 different models of the atom, going from solid sphere back with Dalton, all the way up to quantum mechanical, or you may have heard it called the electron cloud, with Heisenberg, Schrodinger, and de Broglie. So in Dalton's model of the atom, he did not think that there was anything else present in the atom, that there weren't any subatomic particles. As we were able to develop additional experimentations with atom, Thomson came up with the plum pudding model, and determined that there were indeed particles present, but they were fixed, the electrons, and that the rest of the atom was just positive matter, and he was able to determine this using his cathode ray tube experiment. Rutherford took it a step further. He worked a lot with radioactivity and was able to use his gold foil experiment to determine that there was a small positive center to the atom and that the electrons, for the most part, just had to be fixed outside of the atom, and the rest of it wasn't doing a whole lot. So we've gone from having nothing in our atom to now having particles in our atom to now having a nucleus. Bohr was the first one to introduce the idea of the electrons moving with the assistance of Planck, that the electrons could move between orbits. But his model was only applicable to hydrogen. It didn't work mathematically for the others. And that's where the trio of Heisenberg, Schrodinger, and de Broglie came along. And based on the different characteristics they were able to describe, we have, at this point, determined that electrons are more likely to be found in generalized regions about the nucleus. And we call those probability regions orbitals. Dalton's model was first developed in the early 1800s. The rest of these came about in the late 1800s to the early 1900s. And close to 100 years later, we still, for the most part, we might be doing some slight refinements with our quantum mechanical model, but we still hold most of it still today is what we thought it was back then, over 100 years ago. So I think it's kind of amazing how science, we've been able to look at things on a much more microscopic level, but that these scientists back then can't open an atom, were able to develop experiments to better ascertain what was taking place. And as we find more information, if we need to refine our model more, we'll do so. So just some highlights. Democritus actually was a Greek philosopher who first came up with the idea of the atom, but Aristotle stomped all over it and pushed it away for over 5 centuries. I told you how Dalton brought it back. One thing I think is really neat about Dalton, he was the first scientist to actually describe what he thought was happening with the atom, the first atomic theory. And although there definitely are attributes to it that do not apply anymore, we know that atoms are not indivisible. We know that atoms of an element aren't all the same because of isotopes, but the latter 3 are still true. That we know different elements have different, that their atoms cannot be the same, that compounds will always exist of the same relative amounts and kinds of atoms, and that you can create or destroy them. Pretty freaking amazing to me. I talked to you about Thomson and Rutherford already. Rutherford also was able to figure out about the proton. Bohr showed that the electrons move with those quantums, which he was able to do through Planck. And then the trio that make up the currently accepted model, Heisenberg, was responsible for determining that you can't tell where something is and in what direction it's going to be moving. You can't do both of those precisely at the same time. You can do one or the other, but not both. De Broglie showed that particles can act like waves and waves can act like particles. so that they were not distinct entities from one another. And then Schrodinger gave 4 characteristics that we'll spend more time on later that he used to describe where we're likely to find those electrons at in the orbitals. I told you about protons and electrons. Chadwick worked with Rutherford. He was also able to determine about the neutron. And then Millikan determined the fixed amount of charge that electrons are able to transfer with his oil drop experiment.